So question 2 is about hydrolysis, and first of all it wants to know what that means. So it just has this very vague meaning. It's not a very precise word, hydrolysis, but it just means a reaction in which a compound is broken down by reaction with water. And that's interpreted fairly loosely. So it includes aqueous acid and aqueous alkali in that sort of vague term water there. But it must be aqueous, that's the important thing. So when you write conditions down, as in this case, the main reaction you learn is with sodium hydroxide, but crucially it's aqueous sodium hydroxide because it's got to fit that definition. Okay, so then it wants an equation for the hydrolysis of 1-chloropropane. So that's propane, 3 carbons. So 1-chloropropane is that, with aqueous sodium hydroxide. So you can either do this as an ionic equation or as a full equation. So I'll just write both up and then you can choose. So in other words, you can either put NaOH or you can put OH minus there. And it's just a substitution. So where the Cl was, you get OH instead. So you get that, and that would be the same regardless of how you draw it. And the only difference is that if you write the full equation, you get NaCl as the other product, or if you write the ionic equation, you just put Cl minus. So either of those would be absolutely fine for your equation. And then it wants the mechanism. So this is the simplest of all the mechanisms that you learn. So you've got the polar bond there first of all. So that's really important because it's that dipole that you can picture attracting in the hydroxide ion, and specifically it's that delta positive carbon that's going to attract in the negative charge of the OH minus. And what the OH minus has in particular is a lone pair of electrons. In reality that oxygen has 3 lone pairs, but we just draw in the 1 because it's the 1 that's going to mount the attack. And so it uses that lone pair to attack the delta positive carbon, and you draw the curly arrow like that, so it must come from the lone pair to the carbon that's being attacked. And as we've seen now in electrophilic addition as well, as one pair of electrons moves in on a carbon like that, it will generally nudge out another pair, and so this bond breaks at the same time as that one's forming. So you draw a curly arrow from the middle of the bond out onto the chlorine like that, and that pair of arrows represents the pair of the 2 pairs, well, so that represents this pair of electrons moving, so the 2 arrows represent the 2 pairs of electrons moving simultaneously, and that's it. The whole reaction is then complete, because you can see that this curly arrow tells you a new bond will have been created between the carbon and the oxygen. So we have that, and that bond will have gone, but the pair of electrons that was that bond is now going to be a lone pair on chlorine, and that chlorine has become Cl minus because it used to just have a half share in this bonded pair, but now it's got both those electrons to itself, so in effect it's got 1 more electron than it had, so it's Cl minus, and that's the whole mechanism. So as it tells us in the question, this is called nucleophilic substitution, and the reason for that is that OH minus, the thing that's doing the attacking, is an electron pair donor. And that's the meaning of the word nucleophile. Okay, it means an electron pair donor. What type of bond breaking? Well, you can see that when that bond breaks, both of the electrons go out onto the chlorine. That's what the curly arrow means. The carbon gets neither of them, and that's heterolytic fission. Okay, homolytic is when you get radicals, when the electrons get shared out equally, but that's not what's happening here, and the curly arrow shows you that. So this is an example of heterolytic fission, is the answer to part 3. Question 3 then is about the reaction of 1-chloropropane with water this time rather than with OH minus. And the reaction is basically the same. So you get the same product, which is propanol, the alcohol there. But the difference, of course, is that the other product, because instead of getting sodium chloride, which we got with sodium hydroxide, you get hydrogen chloride, so you get HCl being formed. So you can write the equation like that, although because it's in aqueous solution, remember that those ions will actually be separate, because that's what ions do from an acid in aqueous solution, that they exist separately. So you could also write the equation like this, and that's quite a useful way to write it in the context of the experiment that's coming up, because it emphasises that when the reaction happens it liberates chloride ions in aqueous solution, and that's the key to the experiment that we're going on to talk about. So you can write it either way, just as HCl or as that, but it's worth at least making sure you understand that forming aqueous HCl means that you form aqueous chloride ions. So then it gets on to this experiment. So this is the sort of classic experiment that you need to know for investigating the relative rate of hydrolysis of the different haloalkanes. So it tells you about this mixture that you make, which contains the haloalkane, the water, silver nitrate, which is going to be for testing for the chloride ions being, or bromide or iodide ions being formed, but also ethanol. And the first question is, why do you need ethanol? And so the answer is that it's a solvent. So this is really a clever trick, because you know from the stuff we've talked about intermolecular forces that this compound will not be soluble in water because it can't form hydrogen bonds. And that's a problem if you're trying to do this experiment, because it means that you'll get two layers. So the silver nitrate will be dissolved in the water, this will be a separate layer, and the rate of reaction is likely to be controlled by how good you are at shaking it, by how efficiently you mix the two layers and therefore let the water react with that. And that's not very good when you're comparing rates. So you get round this by using ethanol, because this dissolves in ethanol and so does the water and the silver nitrate. So you're able to get everything in solution in a single layer, and that means you don't have a mixing problem, so you can much more meaningfully compare rates. So you'd have to explain that in detail, but you do need to know that ethanol is used and that it's there as a solvent. And then it wants to know why the tubes are incubated in the same warm water bath. So this is just to make sure that they're all at the same temperature. It's as simple as that. Okay, so to ensure that the temperature is the same, and the reason for doing that is because the rate of reaction is strongly dependent on temperature. And that's something we'll learn much more about when we get on to rates of reaction. But it's worth just emphasising here that rates depend strongly on temperature. So obviously if you were comparing them at different temperatures, the difference in rates would be a bit meaningless. So it's what you might have in the past called a fair test. So then part 3 wants to know what's the answer, what is actually the order of reactivity. And the answer is this, that this one reacts the fastest, the iodo compound, and then the bromo one is a bit slower, and then the chloro one is the slowest of all. So that's the order of reactivity. So fastest and slowest. And how would you know that? Well, it's because, remember, as soon as these halide ions, the chloride ions in this case, or bromide ions, or chloride ions, or iodide ions, as soon as those are formed, they precipitate out, because the reaction between those ions and the silver ions is really, really fast. So effectively, the rate at which the precipitate appears is controlled by this hydrolysis reaction. As soon as the ions are formed, they precipitate out. So you just monitor the rate at which the precipitate forms. So the answer is that the silver iodide, which is a yellow precipitate, remember those colours from last term, forms fastest, and then silver bromide, which is cream, and then silver chloride, which is white, forms slowest. So that's the observed outcome, and that's what it tells you about the reactivity. So then it wants the two equations to describe what happened to produce that observation. So the first one is just the iodo analogue of that one. So the first reaction is 1 iodopropane plus water gives you propan 1ol plus H plus I minus. So that produces the I minus ions, and then immediately you get the second reaction, and just write the ionic equation for this. Okay, don't try and write a full equation. Ionic equations are clearer, simpler, better. Okay, so try and get used to using them. So the silver ions meet the iodide ions, and they just stick together to form the silver iodide, which is your yellow solid. Okay, and that's a really important experiment. So you get asked both about the practicalities, but also you need to know what the result is. Part 5 is asking us for an explanation of this order of reactivity, referring to these numbers, which are bond enthalpies. So bond enthalpy is something we're going to learn about in the next section we come on to, which is about enthalpy in general. But what it means is it's actually the energy required to break 1 mole of these bonds in the gas phase. Now, the gas phase isn't directly relevant here, but it's defined that way to keep things simple, to take out any complicated effects resulting from, interaction with solvent and so on. But it doesn't matter, because all that matters about it is that because it's the enthalpy change required, the enthalpy change when a mole of bonds is broken, the bigger the number, it means the stronger the bond. So that's all you need to really get from that. So we may as well say that the higher the bond enthalpy, or the bigger the bond enthalpy, the stronger the bond. And so we can see that the correlation here is that CCl is the strongest, which means hardest to break. And if it's the hardest to break, it means that the rate of hydrolysis which involves breaking this bond so the rate of hydrolysis is the slowest. Okay, so that's the correlation, that's the strongest bond, and that's what the numbers tell you, because it's got the biggest number there, so it needs the most energy to break it, and therefore it's the hardest to break, and therefore the rate at which it's broken is the slowest. And that's actually enough to answer the question. Conversely, you could say that Ci is the weakest and therefore reacts the fastest. If you want to put it in a bit more detail, you can do by saying that the activation energy, and again this is something we'll talk more about later on when we talk about rates of reaction, but the activation energy for hydrolysis decreases in the same order as the strength of the bond. So the haloalkane is the strongest, is the highest activation energy, and then the bromoalkane, and then the iodoalkane, where R just means the organic group, which could be a methyl group or whatever. Okay, and that term activation energy is something we'll start using much more when we've talked about rates of reaction. So the idea is that it's the energy that needs to be put in to get the reaction going, and that generally means the energy required to break some existing bonds. So in this case, because we have to break the carbon to halogen bond, the stronger it is, the more energy you have to put in, and that means the less likely it is to happen when molecules collide. Hence the reaction goes more slowly. So that's a sort of bit of added detail, but that's enough to get you the marks in a question like that.